Hello, the topic of our discussion in this video tutorial is closed sets. Before I give you the definition of the closed set, I need few important notions and first I will define what is a limit point. We say a real number x is a limit point of a set A if and only if for all epsilon positive we have the epsilon neighborhood of the point x. If I take the intersection with the set A, this contains at least one element other than x. Or in other words, if I take the intersection of x, the neighborhood of x, if I delete the x point from that set and then I take the intersection with the set A, that intersection must have at least one element, or in other words, this intersection is non-empty. And this neighborhood, which is basically does not contain the element x, is also known as the deleted neighborhood of the point x. Next, I will give you the few example of a limit point. My first example is I will consider the set A as my open interval 1 and 3. So for example, if I pick a point 2 which is belong to this set, or which is the basically the midpoint of that interval 1, 2, 3, and then I can prove that 2 is a limit point. To prove this, I need to pick an arbitrary epsilon strictly positive, and then I will take this neighborhood of 2. In this case it will be 2 minus epsilon and 2 plus epsilon. And if I take the intersection with the interval 1 comma 3, and that intersection must be non-empty. As you can see that if I take the epsilon less than or is equal to 1, my intersection will be 2 minus epsilon and 2 plus epsilon. And if I take the epsilon strictly greater than 1, then the intersection will be 1 comma 3. In both the cases, this intersection contains at least one element which is not is equal to 2. Therefore, this intersection is non-empty and it contains the at least one element which is different from 2. So this implies the 2 is a limit point. Therefore, 2 is a limit point. On the similar idea, you can also prove that every element of this set is a limit point. In the second example, we also show that the element 1 is a limit point of A. Clearly, 1 does not belong to the interval A, because 1 is the end point of that interval, which is not the part of the interval 0 to 3. So this is, let's suppose this is a 1, this is a 3. Now what I need to show that if I pick any arbitrary number epsilon and then I take a neighborhood 1 minus epsilon and 1 plus epsilon, if I intersect that neighborhood with 1 comma 3, and I need to prove that this neighborhoods contain at least one element which is different than 1. So as you can see that if I take an epsilon which is less than or is equal to 2, then this intersection will contain start from open interval 1 and it is other endpoint will be 1 plus epsilon. And if I pick the epsilon strictly greater than 2, then this will be simply 1 comma 3. And both the element contained at least one element which is not is equal to 1. Therefore, this intersection is non-empty and it contains an element more than just 1. So therefore, 1 is a limit point. Similarly, you can prove that 3 is also a limit point of this set. Next, we will take another example. In this example, I will consider the set A, and there its elements are 1, 1 half, 1 third, and so on. So it means the reciprocal of all the natural number where n belong to the set of natural number. And I will claim 0 is a limit point of A. So to prove this claim, first I will pick an epsilon, arbitrary epsilon, strictly positive, and I will create a epsilon neighborhood of this point, which is a simply minus epsilon and then the plus epsilon. And then I will show that if I take the intersection of this interval, uh, which does not contain 0, if I actually subtract the 0 from this open interval, and then I take the intersection with A, that intersection is non-empty, or in other words, the open neighborhood V epsilon of 0 and the A contain at least one element which is not 0. So to prove this intersection is non-empty, I need to show that both the interval contained one common element. Since epsilon is strictly greater than 0 and I can find a natural number by using the Archimedean property, so that 1 over that natural number is less than epsilon. And this simply implies that 1 over n absolute value of this is also less than epsilon, or in other 1 over capital N belongs to this open interval minus epsilon and plus epsilon. So this shows that the epsilon belong to, this shows that 1 over n belong to this interval. But also notice that 1 over n is also the member of the A, because all the member of A are the reciprocal of rational number. So this shows that 1 over n, so this implies 1 over n belongs to the intersection of A and the V of epsilon, and that number is not 0. So therefore, the intersection of A with the epsilon neighborhood, deleted epsilon neighborhood of 0 is not equal to empty. This shows that 0 is a limit point of the set A. Next, we will prove this important result on the limit point of a set. This theorem says that if X is a limit point of a set, then we can find a sequence AN which converges to this limit point X. And that sequence will contained in A, and it has a one restriction, that this sequence must not be, all the term of this sequence must not be is equal to X. So let's begin the proof. So since the theorem has if and only if a statement, so I have to prove the forward direction and then I will prove the backward direction. So first write down what we need to prove for the forward direction by writing what is given. So the given is X is a limit point. X is a limit point of the set A. This is given. And what we want to show, actually in this case we want to construct, so we want to construct the sequence AN which is belong to the set A, and this sequence AN has the property that all the element must not be is equal to just X, and this sequence satisfy this property, the sequence AN converges to X. So this is, we want to construct a sequence which is converges to our limit point. So we will start from what is a given. So X is a limit point and I will use the definition of the limit point. So since X is a limit point, it means for all epsilon we have if I take the epsilon neighborhood of this point and I take X away from this neighborhood or this interval, and then I intersect that with A, then that intersection will be non-empty. So this is the definition of the x is a limit point. And this statement is true for all epsilon. So it must be true if I take epsilon is equal to 1. This must be true if I take epsilon is equal to 1 half, if I take epsilon is equal to 1 third, and so on, if I take epsilon is equal to 1 n, and so on. So, or in other words, this implies if I take the neighborhood of radius 1 of x, and then I take x away from this and I intersect with this basically a, that will be non-empty. Similarly, 1 half x away from x intersection a will be non-empty. Similarly, v 1 third of x other than x intersection a is non-empty. And similarly, v1 over n x n intersection a is non-empty. So next I will construct my sequence an by picking a1 from the first set, a2 from the second set, a3 from the third set, and an from the nth set. Or in general, this implies the sequence an, each term of the sequence belongs to 1 v1 1 over n x intersection a, where an is not equal to x. Or in other words, the sequence an is belongs to a and an is not equal to x. So we are able to find a sequence so that the each term of the sequence belongs to a and each term is different than x. Next we need to prove that this sequence is converges to x, which is the limit point of our set A. We claim the sequence which I constructed, this is sequence in fact converges to x. So next we have to prove this claim. To prove this claim, first observe the element an is belongs to this neighborhood 1 over n x, and this implies the distance between an and x is less than 1 over n. This is by the definition of epsilon neighborhood, because epsilon neighborhood is a interval whose length, whose radius is 1 over n, and since an belongs to that interval, that means the distance between the center and an must be less than 1 over n. So now I will use the Archimedean property. So by Archimedean property, I can find a natural number n, so that 1 over n is less than epsilon when n is bigger than or is equal to that capital N. So there exists this capital N by Archimedean property, so that we can make 1 over n less than epsilon when I take n bigger than or is equal to n. What we show that for all epsilon greater than 0, there exists capital N by Archimedean property such that a n minus x is less than epsilon when n is bigger than or is equal to capital N. So this implies this sequence an is converges to x, which proves the claim. And also this proves the forward direction of our theorem. Next we will prove the reverse direction of our theorem. So to prove the reverse direction, first I will write down what is given. So the given is you have a sequence an, which is each term of the sequence belongs to our set A, and each term of that sequence is different than x, and this sequence has this properties converges to x. So this is given, and what we want to show, the x is a limit point of A. So first we will start from what is given. So the given is the sequence an converges to x. So I will use the definition of convergence. So convergence means for all epsilon positive, we can find a natural number n, capital N, so that the difference between an and x is less than epsilon when little n is bigger than or is equal to that capital N. So since this statement is true for all n bigger than or is equal to n, so in particular this statement is also true for when n is equal to that capital N. Or in other word, the a capital N minus x, this is also less than epsilon, and this implies minus epsilon less than a capital N minus x less than epsilon, and this implies minus epsilon plus x less than a capital N less than epsilon plus x, and this implies a capital N belongs to this open interval minus epsilon plus x and epsilon plus x, and then in fact this is the epsilon neighborhood of x. This implies a capital N belongs to this epsilon neighborhood, and definitely a capital N is not equal to x. Since a capital N, which is also given that this is the member of that set A, so this implies a capital N belongs to the intersection of a epsilon x, which is, if I delete the x even from that, and a. Or in other word, this neighborhood, when it intersect with a, is non-empty. And basically this is the definition of a limit point. So this prove x is a limit point of a, and this complete the reverse direction of our theorem. Next I will give you the definition of what is a isolated point. We say a element A of the set is an isolated point if and only if A is not a limit point. For example, if I write down this set 1, 1 half, 1 third, 1 4, and so on 1 n. In this case, 1 half is an isolated point because I can show that 1 half is not a limit point of this set. Finally, I will give you what is the definition of a closed set. We say a set, let's suppose f, which is a subset of real number, is closed if and only if f contains all it is limit point. Let me give you a few examples of closed set. For example, this interval 1 comma 2, this is a closed set because every point of this set is also the limit point of this set. This is not a closed set, 1, 1 half, 1 third, and so on is not a closed set because as you can see 1 half is the member of this set, but 1 half is an isolated point or in other words is not a limit point. Another example of a set which is not a closed is this is not closed. Again the reason is 1 is the limit point, 1 is a limit point, of A, but 1 does not belongs to A. So a closed set must contain all its limit point. If you find a limit point which is not the member of the set A, then you can basically say that that set is not a closed set. Next, I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.